welcome to lecture 4. Today we will study about the kinetic properties. Now, kinetic properties. Usually this kinetic property is used to detect the stability of the system, molecular weight of the particles and the transport kinetics. And what is included in this kinetic property? We include Brownian motion, diffusion, sedimentation, viscosity and colligative properties. Brownian motion. Robert Brown has given a theory which states that colloidal particles, when it is less than 5 micrometer, they continuously shows random motion, and this random motion is due to the thermal energy. And when they are in this zigzag random motion, they collide with the wall, they collide with the other particles, and due to this collision there is a change in direction, there is a change in velocity, and these changes can be captured by your light microscope, and the particles moves against the concentration against the gravitational force. They move against the gravitational force, and these Brownian motion stops when the size of the particle increases and the viscosity of the medium increases. Now, before starting this diffusion, I want to add certain points in this Brownian motion. This Brownian motion is responsible for the stability of the colloidal particles, because as we know there are mainly, we will discuss mainly related to lyophobic colloids and lyophilic colloids. In both the cases, what happens in case of lyophilic colloids, what happens, the solvent sheath is formed, and this solvent sheath which is formed on the particle, it prevents the two dispersed particles from coming in contact with each other, and as they are not coming in contact with each other, they do not form aggregates, and they continue the Brownian motion, and this Brownian motion is responsible for the stability of lyophilic colloids. Similarly, this Brownian motion is also responsible for the stability of lyophobic colloids, but the difference is in case of lyophobic colloids, here charges are present on the surface of the particles. So, due to the presence of same charge on the surface of the particles, like charges repel each other. So, as the charges are there on the surface of the particles, so two particles repel each other. As these two particles repel each other, the particles do not aggregate and the Brownian motion is maintained. So, if a system in a system of, especially in case of your dispersion systems, if the Brownian motion is maintained, then the colloidal dispersion systems will be stable. Then comes the diffusion. Now, these colloidal particles are of small size and they pass through the pores, they can pass through the pores plug in, and this may because of the Brownian motion. And as we know that in diffusion we have two laws are there, Fick's first law and Fick's second law, and we will just discuss about the Fick's first law. This Fick's first law states that the particles diffuse spontaneously from high concentration region to the low concentration region. And how long does these diffusion takes place? Until the diffusion equilibrium is attended. And the application is here the molecular weight is determined. We can use this diffusion to find out the molecular weight. Now, diffusion is equal to R T divided by 6 pi eta n cube root 4 pi n divided by 3 m v. Now, R is your gas constant, T absolute temperature, 6 pi is a constant, and this eta is your viscosity, this n is your Avogadro's number, m is the molecular weight, and v is the partial specific volume of the particle, and this formula, by using this formula we can find out the diffusion. D is your diffusion coefficient of the polymer. So, from this we can find out the molecular weight also. Now, in diffusion experiment, when we are taking dQ is the quantity of drug diffused and D is the diffusion coefficient, S is your plane area, and dC is the concentration change, dx is the distance travelled, and dt is time taken for diffusion. So, dq, that is the quantity of drug diffused, is equal to minus d, that is diffusion coefficient, multiplied by the surface area divided by dc by dx multiplied by dt. And Graham's law of diffusion states that the speed of diffusion is fast for crystalloids like salt, acids and base, and speed of diffusion is slow for colloidal substances like gelatin and albumin. Then comes sedimentation. This is influenced by the gravitational force and it is applicable for particle size when the particle size is greater than 0.5 micrometer, and this can be explained by Stokes' law equation, and here it gives us the velocity of sedimentation, but there is no sedimentation if there is a Brownian motion. And yes, in this case also, so we can do forced sedimentation, and it is done to estimate the molecular weight of the polymers. And how it is done? It can be done by using ultracentrifugation. Then comes your these are mainly applied, the sedimentation method, it is forced sedimentation is applied to find out the molecular weight of the particles and to study the micellar properties of drugs and the molecular weight of the micelles. Then comes colligative property. As we have already studied that colligative property are the properties which depends on number of particles. It depends on number of particles present in a system. Okay. And here mainly osmotic pressure is suitable here to measure the molecular weight of dispersed particles. There are 4 types of means under colligative properties, we know that there are 4 colligative properties are there, but here for colloidal preparation we are only concerned we are only taking into account the osmotic pressure. Osmotic pressure is required, or it is suitable to measure the molecular weight of the dispersed particles. Then comes viscosity. It is a very important parameter, viscosity. Viscosity, it is affected by many parameters, like first the shape of the dispersed particles. If the dispersed particle is spherical, then the viscosity decreases. Why? Because we know that spherical particles have minimum surface area. So, when the surface area decreases, and we know that viscosity is a frictional force. So, when the surface area decreases, then obviously the viscosity will decrease. So, the particles when have spherical structure, their viscosity decreases, and particles which have linear structure. Linear structure means more contact points. More contact points means more affected by the frictional forces. So, the viscosity increases when it have a linear shape. Then comes affinity of the particles to medium. If these linear particles have low affinity, if the linear particles which are placed in a medium have a low affinity, then they will assume a spherical shape. Spherical shape means if the disperse phase has low affinity toward the dispersion medium, then it assumes a spherical shape. Okay? And as it assumes a spherical shape, the viscosity decreases. As we have studied that it is a tendency of any molecules to get attracted towards the other molecule which is of the same nature. Suppose we are using a polar dispersed phase, then it gets attracted toward a polar dispersed medium. Okay? But if the affinity between your dispersed phase and dispersed medium is less, then what happens? The dispersed particle will try to arrange its structure in such a way, the molecules will try to arrange the atoms in such a way that it comes in minimum contact, it comes under minimum contact with the dispersed medium. So, it tends to be spherical. So, as it assumes or takes a spherical shape, the viscosity decreases. Then comes the type of the colloid dispersion. As we have studied that lyophilic colloids which have higher viscosity compared to that of the dispersion medium. Why they have higher viscosity compared to dispersion medium? Because these lyophilic colloids, they have greater affinity towards the dispersion medium. The particles, the dispersed particles which forms this lyophilic colloids, they have greater affinity towards the dispersion medium. So, the viscosity of the colloidal preparation is greater compared to the viscosity of the dispersion medium alone. Then this lyophobic colloids. In case of lyophobic colloids, the viscosity remains almost same as that of the dispersion medium. Why? Because the interaction between the dispersed phase and the dispersion medium is very less. So, as the interaction is very less, so the viscosity of the lyophobic colloids remain almost same as that of the dispersion medium. Now, the molecular weight of polymers can be found by using this viscosity. Now, higher the molecular weight of a material, greater will be its viscosity. So, by measuring the viscosity of the molecular weight, by measuring the viscosity, the molecular weight of the polymers can be obtained or determined, and the flow of a dilute colloidal system which have a spherical particle can be expressed by using Einstein equation. And what is Einstein's equation? Einstein's equation here, viscosity of the dispersed particle is equal to the viscosity of the dispersed medium multiplied by whole 1 plus 2.5 phi, and this phi stands for volume fraction of the particle. What we understand by volume fraction of the particle? Volume fraction of particle means the weight of particles divided by the total weight of the preparation or the colloidal dispersion, or if we take it in terms of, as here we have taken it in terms of volume. So, we can say that phi is equal to volume of particles by the total volume of the dispersion. So, it is a volume fraction. Now, this equation of Einstein equation can be rearranged to obtain relative viscosity and specific viscosity. Relative viscosity is equal to viscosity of the colloidal preparation divided by viscosity of the medium is equal to 1 plus 2.5 phi, and specific viscosity is equal to viscosity of the dispersion divided by viscosity of the medium minus 1 is equal to 2.5 phi. So, the specific viscosity can be written as the specific viscosity is equal to 2.5 phi, and what is this phi? It is the volume fraction or the fractional volume of the particle. So, what is the fractional volume? We have already discussed, it is volume of particles divided by total volume of dispersion, and it is represented by concentration. We can represent it by concentration. So, in place of this phi, we can write the concentration term, that is C. So, we can rearrange this, then we will get specific viscosity divided by C is equal to 2.5, and this 2.5 can be taken as K constant, that is your intrinsic viscosity, and molecular weight can be determined by using this equation, that is viscosity is equal to K, this will be capital M to the power A. This K and A are the constants of polymer and M is the molecular weight of polymer. And if we plot a graph between the specific specific viscosity divided by concentration versus concentration, then this K, that is intrinsic factor, can be obtained, and this can be used to calculate the viscosity. Then comes the, and from this we can also find out the molecular weight. Then comes your electric property. Electric property of colloids, it is a very important one. We have already discussed how these charges are created on the surface of the particles. The charges can be created due to three causes. One, if there is a functional group which is present on the surface of the dispersed phase, it get ionized, then there can be charge can be there on the surface of the particles. Second, if the ions which are present in the dispersion medium get adsorbed on the surface of the particles, and here even in case of pure water, the hydroxyl ions and the hydronium ions also get adsorbed on the surface of the dispersed phase, and this may be these 2 points mainly contributes to the presence of charges on the surface of the dispersed phase of colloidal system. And so, this surface charge is a important measurement. Why? Because this measurement helps us to find out or to predict the stability of the system, of the colloidal system, and mainly this stability is denoted by your zeta potential. Actually, zeta potential tells us about the electrical of the electric potential which is present across the plane of shear and the electroneutral region. Actually, this is it gives us the potential difference which exists between your plane of shear and the electrically neutral zone or neutral layer. Okay. And to understand this, we can take an example. Suppose this is our particle, okay, and this is a solid surface, and yes, we are discussing about colloids, and the main condition is your dispersed phase should be immiscible with your dispersed medium. So, the particles, solid particle, when it is kept inside a dispersed medium, it is not soluble with the dispersed medium, and suppose it has charges as it is placed on the placed inside the dispersed medium, charges are created on its surface. Okay. So, as it has positive charge, we have taken example that positive charge is there on the surface of the on the solid surface, it can be negative charge also. So, we are taking just a example. So, if there is positive charge, they will attract the negative charges. So, the layer which is nearer to this, it will be tightly bound with this molecule, okay. And here you will see that the number of positive charge is more compared to the number of negative charge. So, this is your tightly bound layer, but as here the positive charge is still more compared to the negative charge, still it has the ability to attract some negative charges, but in this layer some positive charges will also be attracted, okay. But this layer is a tightly bound layer, but as the distance from the original surface increases, the charge it becomes more diffusal, the layer become more diffused, and here this is your tightly bound layer, and this is your diffuse layer. This is your diffuse layer. Just a minute. And this is your diffuse or diffusion, diffuse layer. Diffuse layer. So, as this is a diffuse layer means these are not tightly bound layers. So, we use this layer, this is your plane of shear, this is the plane of shear. Then after this we will have a region of which is electrically neutral region, So, the potential difference is measured. So, the potential difference is measured between your plane of shear and the electrically neutral region, electrically neutral region, and this will give you your zeta potential. Now, we use this layer, but this is not the original layer which is present on the surface of the solid. Why we use this layer? Because this layer keeps on moving as this particle keep on moving. Okay. So, this we measure this potential difference, and this is your zeta potential. So, we will continue with this electric property in the next lecture. Thank you.